Hey guys, Mr. Riz here to help you out on the 6.1 notes here for the first part, and we're going to be looking at graphing growth functions and decay functions. So what we're going to do is look at new types of functions that are called exponential functions. Exponential functions always start out, and we're going to first look at exponential growth functions where we have f of x equals some number to the x power. And so in this example, they use b. To be an exponential growth function, that number b has to be bigger than 1. So we can start out with like 2 to the x power or 5 to the x power and go through. Now, there ends up being 3 critical points on there. And what we're going to do is kind of go through an example to explain those 3 critical points. Okay, so let's go through, and this first example here, we'll do y equals 3 to the x power. We're going to plug these in and just kind of show you what this. So let's start this off. If we'll start out easy here. We'll start out with 0. Okay, if I plug 0 into this, okay, y equals 3 to the 0 power. If you don't know what that is, plug it into the calculator, but anything to the 0 power is 1. So if we were going to graph this equation out here, all right, at 0, we'd be at 1. All right, next we'll plug in 1. What's y equals 3 to the first power? 3 to the first power is 3. So over 1, we'll go up to 3. 1, 2, 3. All right, next we got y equals 3 to the second power, and that would be 9. So over 2, we'll go up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So way up there. So you see the graph kind of starts up and goes higher, higher. And the next one would be like 27. And so it really jumps up. Oh, I was putting the wrong numbers here. This should be 3, and this should be 9. Okay, next, if we plug in -1, y equals 3 to the -1 power. Well, the -1 power, if we remember, just turns it into a fraction, so it's going to be 1 over 3 to the first power, or just 1 over 3. So that would be negative, or be 1/3. So it's still a positive number, it's just over here at like 1/3. And then if we go to -2, that'd be y equals 3 to the -2nd power, which is 1 over 3 squared, because the negative sign puts it on the denominator, and 3 squared is 9. So putting these in the wrong spot is 1/9, which would be even further down. Now, the graph would keep going lower, 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 but it would actually never end up reaching to 0. So if we want to look at the domain, remember the domain is how far left and how far right we would go. The domain would be actually from -infinity to infinity, because we could plug in every number all the way to the left. I mean, we can plug big numbers in here. So even though it just keeps going up to the right, or keeps going up, I mean, we could plug in 10, 3 to the 10th power, some crazy huge number, but we can plug in any number. Now the range, this definitely, you can see, goes all the way up towards infinity. So we know it's going to end at infinity. The bottom, though, we get lower, lower, lower. We get 1 over 9 and 1 over 27 and 1 over 81, and we keep getting lower, 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 smaller, smaller numbers. We're going to get close to 0, but we're not going to include it. So the range is from 0 to infinity. Okay. So this is a parent function here, and just to make sure we know the parent function and what it does is that this a number here is our constant, is the leading coefficient. So what this a number will do, will flip this up or down, or vertically or horizontal. So if a is positive, we'll make a note here. What the graph will do is look like that. It will like swoop from left going up. And if a is negative, we would have a graph that goes down. So they'll start out flat. All right, what h does is a shift left and right. So our graph would just, start off here in the middle, and then it could potentially like shift over, shift to the right. So it still goes up, but we just shift it over more. And then k is a vertical shift. So normally our graph looks like so. If we had some k, it would do the same thing, but higher up on the graph. Okay, so let's look at this problem here, and we'll do this as a graph. We'll graph it out, and then we'll state the domain and range. Clear this off so we got some more room here. All right, so it doesn't hurt to graph we go through this. All right, so let's plug in 0 first. All right, so this would be 2 to the 0 power plus 1, or 1 plus 1, which is 2. So 0, we're up at 2. All right, now let's plug in 1. So 2 to the first plus 1. So 2 to the first is 2, plus 1 is 3. Yep, so 1, 2, 3. Not too bad. All right, let's plug in 2 squared. 2 squared plus 1. So that'd be 4 plus 1. Okay, that goes up to 5. So 3, 4, 5. We can keep this pattern going, but you can see it keeps going up to the right. All right, now if we plug in -1, 2 to the negative first power plus 1, that'd be 1/2 plus 1, or 1.5, or 3 over 2, if you like fractions. So that would be 1.5, which would be right here. And then let's see here, 2 to the negative second power plus 1 would be 1/4 plus 1, which would be 1.25, or 5 over 2. So still just a little bit more than that. Now, what ends up happening is this graph gets flatter and flatter and flatter, but it actually never crosses on 1. So the domain is still negative infinity to infinity. It still goes all the way to the left, and then would keep going to the right. Now the range keeps going up towards infinity, but we would actually never get lower than 1. So this k number will always represent the lowest part of our range. All right, so we actually don't need to, well, we can graph it if we want, but we can go through here and find some of these things out. So our a is -2, our k, let's see, our k is +2, and because it's x minus k, and then our h, and then our k is 0. So if you think about it, our normal graph would go so, but this one over here is going to be, instead of being right here like that, we are going to do a couple things. We are going to flip it over because we have the -2, and we are going to shift it 2 to the right. So it's going to be negative and shifted 2 to the right. So it should do something like this. Now we can plot some of these points out, or we can use Desmos. And let's just open up Desmos to see how well we did. Or I'm going to use this graphic calculator app here that I have. This is kind of easier to show this up. So we think, since it's the -2, like type this in, -2 times 5 to the x minus 2 power. It should be flipped it over and then shifted over to the right. We'll take a look at that. There we go. So it does get shifted over a little bit, not as much as what we normally see, but it is shifted over to the right a little bit and then goes up. So kind of similar to what we did. So looking at the domain here, the domain is still negative infinity to infinity. It goes all the way to the left and all the way to the right. And the range, all right, now the range is going to be kind of backwards, because the highest that this graph goes is to 0, and the lowest it goes is to negative infinity. So when your a is negative, your range actually gets flipped. Okay, the other thing we can talk about are exponential decay functions. So exponential decay functions is when our b number is a fraction, is a number less than 1, and still actually positive. So a b number that goes through here. So if we got 1/4, let's go through this problem here and make sure we understand the domains and ranges of it. So if we went through and try to figure out our table here, if we plug in 0, well, this would be 1/4 to the 0 power. Anything to the 0 power is 1. So if we're looking at our graph here, it still is at 0, 1. All right, let's plug in 1. So what's 1/4 to the first power would be 1/4, or 0.25. I put 1/2 here. 0.25. All right, so that means over 1, we are just barely above that. And then if we plug into 1 over 4 squared becomes 1/16, or like that's really small. So we're very, very close to 0. Now, if we go backwards here, if I have, we start with -2. I guess we'd mix -1 here. Let's put -1 on our chart here. We plug in -1, this would be 1/4 to the -1 power. Now the -1 flips the fraction, so that just becomes 4/1 to the first power, which is just 4. So -1 would go up to 4. 1, 2, 3, 4. And then, okay, what if we plug in 2? 1/4 to the -2nd power would become 4 over 1 squared, or 4 squared is 16 over 1, so that's 16. So 2 goes all the way up to 16, and then -3 would go up. So these exponential decay functions start up high and they end down low. So like a growth function, but backwards. Now the domain is still -infinity to infinity. We can make this graph go all the way to the left and all the way to the right. In the range, well, let's see, the range starts out low at 0 and goes up high to infinity. So the domain and ranges are actually very, very similar. Okay, let's clear this off. See what else we got to do. Okay, so where you typically see these problems are like examples with like exponential growth. We can talk about like populations of the functions or populations of a bacteria, or we can talk about exponential decay with something's decreasing over time. So here we got is an equation that goes through, and we got the consensus in 1790. At that time, the population of the U.S. was 3,929,000, so forth. Since the U.S. has grown approximately 2.3% every year, we could draw a graph to represent that. And the way that we can represent that, any growth here, is to take the initial population times 1 plus the rate of the growth over time. So that would be very helpful for us later on. So say like we had bacteria here, and there's going to be a story that we're going to look at tomorrow. And say we have initially like 10 bacteria. If we know that is increasing at a rate of like 25% a day, we can say that's 1 plus 0.25 to the x power. And so if we have 10 bacteria that increases at 25% per day, this equation here will tell us how many bacteria we have total if we just want to know the days. Okay, so this wraps up this section. Today we're going to be looking at graphing for your homework. So do the 6.1 worksheet A, the graphing worksheet for today, and then tomorrow and the next day we'll be working on a zombie activity. Have a great day, guys. I will see you next time.